astrobiology, we then agreed that I should talk a little bit about everything. So now I'll try to talk about ice and water on Mars and Europa in 15 minutes. So this is the attempt. And I'll just introduce myself. So I've studied geophysics at the University of Copenhagen, particularly glaciology and climate system and the solar system. I wrote my master thesis on the ice shell on Jupiter's moon Europa. And I've been involved in field work in Greenland, Iceland, and Antarctica. I was actually on the expedition with Torstein. And right now I'm doing a PhD on ice on Mars. So I'll just briefly tell you why we look at ice at all. So why we study ice sheets here on Earth and on any planet is because we can get information about the present and past climates. An ice sheet is composed of the precipitation. It's direct atmosphere samples from many years ago. We can find out what past temperatures have been, how the precipitation has been composed, what gases there were in the atmosphere, volcanic eruption history, and so on, dust and circulation. We can also look for traces of life. Søren Mørk, one of the biologists that were here before lunch, is working in a group that works finding fossil life in the ice cores from Greenland and from permafrost in Siberia. I don't know if you can find life on Mars in the ice, but that's not mine. Okay.
Is it okay with the lights on? Sorry. Should we turn them on?
Is it?
No. Is it necessary?
I think it's fine.
Okay, go ahead.
It's okay. So what we are looking at is layers in the ice. I mean, the snow falls from the top, so we have layers covering each other, and we have the youngest one near the surface, and then the youngest one here at the surface, and then the ice is older and older. You can see these very nice layers. This is a radio echo profile from Greenland, and the layers that we can see here on the screen are strongly reflecting layers, and that is that they have high acidity. Layers are also on smaller scales, and we see some persons that have made a double kick in Greenland. So very nicely put down. So let's move to Mars. We know that there is water on Mars in both the ice caps. There are ice caps on both poles, and there is permafrost in the regolith, which is just the upper part of the surface. We also know there's a water vapor in the atmosphere and in ice crystals in clouds. So there's plenty of water on Mars. And this is a picture of the ice caps. We have here the northern ice cap and the southern ice cap. The volume of the northern ice cap is about half the size of the Greenland ice sheet. So it's a big reservoir of water. And they are quite different when you just look at them than the Antarctic and Greenland ice sheet, because they have these spiraling patterns that show that the circulation and the relationship between the climate and the ice caps is somewhat different on Mars than it is on Earth.
Can I ask a question?
Yeah.
So how much of this ice is carbon dioxide?
The bulk of the northern ice sheet is water ice. And the southern ice sheet is also believed to be water ice in the interior. There's a lot of CO2 snow on the surface. I'll come back to tell you why we believe it is water ice, even though we can't see deep down in this ice. I should say that this is about 600 kilometers across and 3 kilometers thick. Same with the southern ice sheet. The southern ice sheet, the visible part of it is smaller than the northern ice sheet. But the southern ice sheet, it's believed that there's a larger area that is an ice sheet. It's just covered by dust. This is a molar map. This is from the Mars Global Surveyor. They have a laser altimeter. This is Mars Orbiter Laser Altimeter, this instrument that measured the topography of the surface. And here you can see one of the differences between the northern and the southern ice sheet is that the elevation of the southern ice sheet is 4 kilometers, some 4 or 5 kilometers higher than the elevation of the northern ice sheet. And that gives a temperature difference between the two ice sheets. And that could explain one of the explanations why we see that the carbon dioxide does not disappear during the summers on the southern ice sheet, but they disappear during the summers on the northern ice sheet. Picture of CO2 snow on Mars. Here we have again the permanent ice cap, and then we see all this white stuff around here. This is snow, and every winter it is so that the atmosphere the winter hemisphere becomes so cold that the atmosphere itself condenses out and forms frost on the surface and snow in the air. So a third of the atmosphere is precipitated out. So there's this huge pressure variation during the year on Mars with 2 pressure maxima and 2 pressure minima. And what you see here on this graph is that this is a temperature scale. Purple and blue is cold and red is hot. And this is the southern hemisphere you see. And the blue color corresponds to CO2 snow. This is the temperature of the sublimation point of CO2. So what you see here is the coming of spring on Mars. So, and you can also see that there's a little bit of blue there at the end in the high summer on the southern hemisphere, and that is because the temperature does not rise above the CO2 sublimation point completely at the southern hemisphere, but they do on the northern. This is a busy graph of the gamma ray spectrometer on the Mars Odyssey. This is actually an instrument suite of 3 instruments, 2 neutron detectors and a gamma ray spectrometer. And what they do is that they look for the signature of hydrogen from the crust. And just to sum up what the result is, that where they find a lot of hydrogen, there is a lot of ground ice. And this is translated into these maps that we humans can read, where it says weight % of water in crust from 100% at the North Pole, and here 57% in areas here around the South Pole, and also up to 11% at equator latitudes. This is a lot of water. So, and it's down in the crust. So, if we can have some, and the temperature here at the equatorial regions, it fluctuates well above the freezing point. So, some depths, it's very likely that we have liquid water, maybe as a film on the grains. So, it was very exciting when these results came out. Nobody believed that there was that much water in the permafrost.
Okay, again, I'm sorry. Because my impression was that isn't the jury still out that it can be hydrous minerals also?
That is true. That is true.
So there's
this is a sign of hydrogen.
Yeah.
Yes, the signature from they find, and so they have translated it into water. Yes.
And what was the energy? The previous slide, there was a peak, a gamma ray peak. But there is no energy scale. Can you tell me what the energy is there?
No, I don't know. But I can give you the reference.
Yeah,
so.
thank you.
Yeah.
I'm ignorant exactly. So why do they send all these rovers up there to search for water when you know there's water?
Why?
Why do they send all these rovers up there to search for water if you already know there's water?
They're searching for life, I think. But we know there's water.
No, they want to find out.
But they also want the proof that it's not just hydrogen from minerals that they see.
Yeah, and
right?
also how long time has it been there? I mean, one thing is having water there for 1,000 years or 100,000 years.
Yeah.
That's not interesting from the point of light, right? You
But
want
I
billions of years.
As far as I'm informed, they have not found water so far. Haven't they? Have they found water with rovers?
No, nobody has actually seen running water. They've seen lots of signs of
Yes.
of running water.
I'll show you some signs of running
But
water.
also it's not only to look for life, it's also to figure out what the detailed mineralogy is, as far as I understand.
Yes.
We don't know that. I mean, one thing is that we can use, and I keep talk.
I'd say it's very interesting. The point, poor speaker, the chance to continue, I think, before she gets distracted, doesn't he?
A big subject here.
Thanks.
Thank you. So this is a close-up on the North Polar ice cap, which is what I'm working with presently. This picture is actually exaggerated in the altitude. It's a composition of the molar topography measurements and a photograph from Viking missions that they put on top of it. And there you can see these terraces in this special pattern of the polar ice cap. But let me show you here one of the profiles. So the molar instrument has been measuring the laser across the surface. And here you can see with the fat line that this is one of these topography measurements of the instrument. And you can see this shape with these terraces. But what you see on with the thin line is a measured profile of the Greenland ice sheet. And that these two overall have the same shape is what gives us the clue that the interior of the ice is water ice. Because if it had been CO2 ice is much softer and it would flow out much faster and be a flatter structure. CO2 ice cannot build up to be more than 3 kilometers thick. It's like putting a drop of honey and a drop of syrup on the table. One flows up quicker. Yes?
You have to wait for Martin gravity, I assume?
No, this is actually no. The gravity comes into play here, but also the temperatures on Mars are colder. So, and then the composition. If there are thin layers of CO2 ice, then we would have this mixture of ice flowing out. But in general, people have been calculating that measured profiles does not correspond to a CO2 ice sheet. Yeah.
I presume that the ice on Greenland is still flowing. Is that the same case here on Mars? It's not
Yes.
a stationary situation. It's still.
This very shape indicates that the ice is flowing because it has this equilibrium shape. It may not, or it indicates that it may have been flowing. It's one of the questions that is not fully answered because the whole mass balance pattern on the ice sheet of Mars has not been fully investigated, and this is also what I'm working with. Torstein.
Did you pick a site on the Greenland ice sheet that gives you exactly the same?
No.
Mass,
No. This is one of the plots from Janus's master thesis.
Okay.
So I just want.
He's the point.
Any more burning questions?
Thank you. So.
Right.
I'm sorry it has to be so superficial. I have the references for everything I'm showing, so please come and bug me in the break, okay? So what you see here is Mars in the northern hemisphere, or northern polar cap again. We zoom in on this square here, and this is one of the terraces, and we zoom in here, and then we see exposed layers. And this is the dream of a glaciologist, to go up there and drill and see, look at these layers, right? I mean, can we find the climate history of Mars in these layers? There's been some attempts of measuring the distance between these layers, making some sort of assumption about the connection between the dust heavy layers and the dust low layers and the climate, and then look at the time scales that we have in the climate system. We know that because of the strong orbital parameters of Mars changes, that the climate on Mars must also change. And so there's been attempts to see if this can be climate signals. So, traces of liquid water. This is about 15-kilometer wide in diameter crater on the northern hemisphere. And this is the equatorward phase, and this is the polarward phase, and then we turn the picture over here and zoom in, and what you see over here are the so-called gullies that are very, very similar to structures here on Earth that are grooved or dug out by liquid water streaming down here. We find them in the north-facing slopes and not in the equator-facing slopes. And this could have something to do with the different temperatures on these two slopes. And this matter is also investigated. Yes?
Can you estimate the age of the crater? Can you estimate the age of the crater?
I don't know what the age of the crater is. Sorry.
But it's on the north hemisphere.
It's on the northern hemisphere. Here's one from the southern hemisphere. This is another looking in this slope here, and here again you see these gullies. Sometimes these pictures can be, you can get the negative 3D effect here, but so these things are dug out, and this is a hill. Okay, so the light source is coming from over here. Okay.
Which way does the water stream there? Does it stream from top to the bottom or bottom?
Yes, downhill.
Yeah.
Sorry, Benny, what was your question?
No, I mean, does it come from the bottom of the picture to the top, or does it come from the top to the bottom of the picture?
It runs this way.
So the rivers disappear instead of going into a wider.
Yes.
So where do they go?
These things, you can find these similar things also on Earth, and this is like it's like a cone of sand that has.
Yeah. Is it deserts you find such pictures where the rivers also
Yes,
disappear?
and on Iceland.
On Iceland.
It's not certain whether the water is coming out in an aquifer between layers or whether.
No, it's not certain if it comes from up here or.
Benny is asking why the rivers actually become narrower as they go down.
That is because of the evaporation of the water.
Yeah. Okay. Yeah. Erosion is like in the Dead Sea region or something.
Yeah, maybe.
Where gullies also feature out.
There's been some speculations that the pressure some few meters or something below causes the water to become liquids, and then it streams out and down.
Yes. It's been calculated that the liquid water is metastable. It's stable for some hours on the surface. So that these features have been formed within a very short time scale. So that you have some layer of water which is at a depth that the pressure is high enough that it can be liquid, and then suddenly someone takes out the plug and the water streams for some hours and form these features.
Right. That actually also explains the fact that the water seems to somehow disappear.
Yes, exactly.
Maybe it freezes up.
Maybe this is 3 hours and then there's no more water. Yeah?
Sorry, what's the scale of the picture?
It's these features are a couple of 100 meters long. Yes. So ice on Europa. This is actually just a little bit of anecdote here. This is a picture that inspired me for my master thesis. So the whole thing about the Europa is that we have these 3 of the inner Galilean satellites, Io, Europa, and Ganymede, are in this orbital resonance. That every time Io has been 2 times around Jupiter, Europa has been 1 time around. Every time Europa has been 2 times around Jupiter, Ganymede has been 1 time around. So they always meet in this lineup. And therefore they can make each other's orbits elliptical. They're all in synchronous orbit, so they always have the same face toward Jupiter. So normally there would be no tidal forces or varying tidal forces. But because we have this elliptical orbit, there are 2 things that come into play. One is that we all know that the speed of the orbit here is faster than it is over here, but the speed of rotation is constant. So therefore there must be this angle variation. Seen from a point of Europa, when you look in towards Jupiter, you are wobbling during orbit. And also the distance between Jupiter and the Galilean moons is varying. So this creates this varying gravitational field, and this creates deformation. So here on Earth, when the moon is passing over us, the solid Earth stretches 20 centimeters, but on Europa it's 35 meters it stretches, right? It's a little bit smaller than our moon, so it's really a big stretch. And this is where all the energy comes from. And there's so much energy that we have these sulfur geysers on the surface of Io, its neighboring moon, the most active, the volcanic active body in the solar system. So this is the famous picture again. This is about 30 by 70 kilometers. And when you just look at it, it looks like sea ice. It looks like floats of sea ice that have been rotating. You can follow patterns of an old surface that has been broken up, and these rafts of ice have been moving relative to each other. Then some people have been measuring, because you know the sun angle in the picture, then they've been measuring the length of the shadows here, and then by isostasy, the principle of Archimedes, you can calculate the thickness of these plates. If you assume the density of the two components, the liquid and the solid component, and you find here that the ice the cover is a couple of kilometers thick.
Are the colors real, or is it?
No, these colors are from the infrared spectrum. So it's a black and white picture with an infrared spectrum. And all these reddish and green colors are actually salt minerals or hydrated salt minerals on the surface. And the very white areas are new and very clean ice, and this is ejected from the crater further south. And it's from one of the very few craters that there are in Europe. There are very few, so the surface is very young. It's believed to be around 50 million years old, plus minus a factor of 5. The structure of the craters, if you look like this, it looks like a frozen-in puddle of water on the surface. So we have these rings of water, very flat structures, and so it hints that there's a soft material below. And for this young surface, we have the proof that most people report. We don't have proof until we land there and scoop up the water, right? But there's liquid water on Europa today is strongly supported by this induced magnetic field we measure around Europa. It has its rotational axis vertical here in the picture, but its magnetic field is tilted 10 degrees to this. So the magnetic field is taking a turn every 10 hours with the Jupiter, and since Europa is 85 hours, it gets overtaken by the equator 8 times per orbit. So therefore, it's 2 times every time it goes around Jupiter. And the Galileo mission of NASA has measured the perturbations of Europa and found that the Europa's magnetic field is an induced magnetic field. It changes its direction depending on where it is in Jupiter's magnetic field. And therefore we have an electrical conducting material. And since the easy explanation for this is this liquid salt ocean. But it's not the only solution, of course, but it's the simplest solution. And therefore we pick it as the reductionists we are, being physicists. So that was it. If I must say, I've been cutting out so much material. I'm sure that's why you have all these questions from me.
It's called Occam's razor.
Yeah. And if you're interested in one of the breaks or sometime, you can come up to me, and I have 7 slides about the missions, the current missions and the future missions for Mars and Europa, and what are their primary instruments for detecting water, ice, and so on.
Oh, it is a prime. There's Titan, Mars, and Europa are the 3 prime places for where you might possibly find life or traces of life that had been in the solar system. So Europa's really.
I'm taking a good look at the picture there. You can see which planet is it.
Any further questions?
Yeah.
Right, Ufo.
I didn't really understand your argument of how you determined how big the ocean, or how deep the ocean was, or the crust was, for how high the ice was. Because if the ice is floating on liquid, I understand that it sticks up.
Yes.
But the surrounding was not liquid, so how do you
No,
use that?
It must have been frozen later. My argument is that you can see that these plates have been assembled before because the pattern fits perfectly like a puzzle. And then you can see this break up, and some of them have been rotating. And rotating and moving a raft of ice demands a soft or liquid medium. So at some time, this picture is sort of a frozen-in picture of the time when it was liquid. It does not say that the ice or that the ocean is liquid today. It only says that it has been at some point. But then you can say, from measuring these shadows, and you can measure the height and so on, from then you can say what was the ice thickness when this area was, when the rafts were moving, when this was liquid.
And when could that have been? Because I mean, it requires that you have liquids almost to the surface around it. Right?
Yes, but the other evidence, this is a lower limit to the thickness of the ice. ice is believed to be from around 5 to 15 kilometers thick, because it can't be thicker due to it still needs to deform in the tidal field. So.
Quick question with that?
Yes, around 20 years ago, people were quite optimistic that the temperature at the base of the North Polar ice cap on Mars could be at the melting point some places.
Yes.
What is your opinion of the status of that question right now with the latest information we have?
I think most people agree now that it's that the ice cap is frozen to the base at the moment. Yeah. But if the climate would change, the ice cap would build up, so it had it would be thicker. Then you can reach the point of melting point at the temperature, because it's a matter of how big a comforter you put on top of the geothermal heat rocks that you will heat up the base.
Okay, thanks very much indeed. Lovely. So now you want to go put down as Odense here, but probably when you sent your name in, as it were, that or you were asked to talk, you were in Odense, but now you're in Copenhagen, excuse me, Aarhus.
Yeah.
Isn't that right?
Yeah.
Yeah. Okay, here.
Okay, so Anna gave me this title.
Sorry.
And as you will hear, most of the data which I'm going to present is definitely on prebiotic molecules, since it's mainly on molecular hydrogen formation on surfaces. But I'll end up by telling how we plan to use these same techniques to study the formation of more complex molecules on surfaces as well. So, since I'm your one here, at the bottom, you can see some of the other people who have contributed to this work. So, as most of you probably know, 123 different molecules have been detected in the interstellar medium or in meteorites, and their complexity range up to molecules containing 13 atoms. Now,